So in this video, I want to talk about damping and what it actually is. So I strongly suggest you watch the videos that I posted earlier on simple harmonic motion, namely the one about simple harmonic motion and the one about energy, because it's going to help a lot with this one. So damping happens because of friction. And what damping essentially is I'm going to use my example of a spring attached to a mass, and we displace it to one side and it starts oscillating back and forth and it has simple harmonic motion. Damping happens when this oscillation it's decreased as time goes on because of the friction that's around it. So we can try to identify some of the frictions that this is going to experience, assuming that this is on a ground, of course. We have the friction here. We also have friction in the spring, because as the spring contracts together and then stretches out, there is amount of work done between the atoms as they kind of like change their spot. And so that's why sometimes heat is produced, assuming that the elastic limit is surpassed. So there might also be friction within the spring itself, which also generates heat and obviously decreases the energy. There also might be some air resistance, which is basically also friction. It's just fluid friction. It's not going to be a lot because it's not like a parachute or anything, but there's still going to be a lot of air resistance between the block and also the springs and the molecules in the air around it. So there is friction, and it's almost very difficult to find an oscillation that has zero friction and zero damping. But usually sometimes the effects are very small and we can change how heavy the friction is, and hence how heavy the damping is, to make results that we want to. So the oscillations decrease as the friction transfers energy away from the mechanical system to the surroundings that they are, and this is when we say that they are damped. So you might have seen in my previous video that there is always energy in this oscillating object. There is kinetic energy that goes around like this, and there is potential energy that is on the opposite. So this is basically going to generally decrease for the object, because this is going to be both of them, both the kinetic and the potential energy is going to be transferred into heat energy because of the friction, and heat energy is basically lost energy. They're dissipated out into the environment. And that's the terminology we use when we describe how damping works. It transfers energy from the system to the environment. So I've mentioned previously that the amplitude of the oscillating object is going to decrease. And this is basically how it's going to look like. So if we were to plot a graph of the displacement to the time, we can see that it decreases like this. And what is interesting is that it doesn't decrease linearly, to say it doesn't decrease at a straight line, but it decreases at a curved line where the gradient is much higher at the beginning. Gradient's much higher like this than at the end where it's like that. So we can see that this is the same for both the below one and the above one. And this reminds me of another graph, which is also our exponential graph, which looks a bit like this. And this is very similar, although this is much more shallow. So therefore, we conclude that the amplitude of the damped oscillations will decay exponentially with time. Exponentially meaning this. And if we were to plot this graph with the x right here, then it would look something like this. And so this is what it's going to be like. Now, why does the amplitude decay exponentially, which means at first it decays at a much higher rate and then at the end it decays at a much slower rate? So why would it be like that and not at a single straight line? Well, that's because, let's picture the oscillating object for a moment. So we have the wall, we have the spring, and then we have the mass. Initially, it's going to oscillate at a very, very high amplitude. And we want to first of all make an observation, is that the frequency of these don't actually change. You can see the width is the same. It's just the height that is becoming smaller. So the frequency equals same. If the amplitude becomes smaller, but the frequency is remaining the same, it just means that initially it travels at a much higher speed because you have to cover a greater amount of distance in the same period of time. So you have a much higher speed, and we all know that the higher the speed, the greater the amount of friction that happens, which means that you're also going to have more energy given out to the environment. So I've written here, big amplitude leads to a higher speed, leads to more energy lost because frequency remains the same. However, when you go to a smaller amplitude, you have to cover a less of a big distance in the same amount of time, and therefore the speed is going to be slower because the speed is going to be distance traveled divided by time. So since the time is same but this has gone down, the speed is also going to go down, and since the speed goes down, the friction is also going to go down, which leads to finally energy also going down. So smaller amplitude leads to lower speed, leads to less energy lost. Hence the decay is exponential. At the higher amplitudes, they lose energy at a higher rate, but at the lower amplitudes, they lose energy at a slower rate. And this is what leads to this sort of graph that is going on here. And that explains the entire phenomenon. So as a conclusion, damping is basically the loss of energy from the system that is in oscillation, in simple harmonic motion, to the environment through friction, which decreases the amplitude of the motion but doesn't decrease the frequency of the motion. So that's about it for damping. It's a fairly simple phenomenon to study, and it's also going to be very useful for the thing that we're going to learn in my next video, which is about resonance and how we can also link resonance with damping. But for now, thank you for watching.